everyone, I'm Navjyoti Sharma, once again in front of you, taking one more complex topic in the subject Fundamentals of Electrical Engineering, which is having a code of BEE 101 under AKTU first year syllabus. So the topic today we are going to take that is the types of energy sources and their source transformation, right? So coming to the types of sources. So basically, we can be having an ideal and practical independent voltage source, or I can be having ideal and practical independent current sources. So broadly, if at all I classify, I may be having them as voltage sources or I may be having them as current sources. First, going with the ideal and practical voltage source, that too independent. That means their values are not actually dependent on any other circuit element, voltage or current. They are independent of their own. So an ideal voltage source is defined as the two-terminal device which is capable of providing a constant current across its terminals, independent of the load current, right? So this is the symbolic representation for an independent voltage source, right? Here, this is an AC as it is varying with respect to the time. So it is a time varying independent voltage source. It is a DC. Then it can be represented like this. If at all I plot the characteristics of an ideal voltage source, in that case, what is going to happen? In this case, if at all I plot the VI characteristics, it is always going to give me a constant voltage across the terminals. These are the terminals, right? So if these are the terminals, it will always going to get me a constant voltage irrespective of the current taken by this, right? If at all I'm having a load over here, right? So what is going to happen? If at all I say there is a load voltage, this load voltage would be equal to the supply voltage, what has been supplied from the source, as there is no drop in between, right? This is expected by an ideal voltage source, that it will always be delivering a constant voltage across its terminals irrespective of the current taken by the load. As the load increases, as we increase the load, the current through the load will increase, right? As we increase the load, the current will also increase. But with that, this terminal voltage is going to remain same as that of Vs. It is not going to get changed. This is what we call it as an ideal voltage source. It can be shown with these characteristics, V and I. It's a constant. It is circuit resistance with respect to time. It is remaining a constant value, right? Now, when it comes to a practical voltage source, if it is a practical voltage source, what we are just saying over here is that the terminal voltage should remain constant, but actually that is not happening in case of the practical. So in a practical voltage source, the terminal voltage is not remaining constant, because a practical voltage source used to have a small internal resistance in series with the source. Because of this small resistance in series with the load, will be having a drop. So as we increase the load, as we keep on increase the load, this load current will increase, and this drop, which is nothing but IL into R, this drop will also increase. So if this drop increases, if this is Vs and the voltage across the load is say VL, then this time I can't say that Vs is going to remain Vs. It is not going to be same. It will be a reduced value. What will be the value of the Vs? Now, in this case, VL is equals to Vs minus this drop. What is this drop? IL into R. That means it's a dropped value. So as the load keeps on increasing, IL keeps on increasing, so VL keeps on decreasing. So compared to a constant graph, what we were getting in case of the ideal one, this time we'll be getting a drooping characteristics, right? So there will be a decrease in the terminal voltage with the increase in the current. So this is what we just discovered in case of voltage sources. Now when it comes to an ideal and practical current sources. Now what is an ideal current source? What is expected by an ideal current source? So what is being expected by an ideal current source is it will always be delivering a constant current through its terminals, irrespective of the voltage across its terminals, right? This is the representation AC. This is the representation for DC, independent. Its value is once again not depending upon any other circuit element, current or voltage, right? Then, if this is an ideal current source, IS, right? There is an infinite internal resistance, right? Because of that, if at all I just see over here, right, at the terminals, if at all I connect a load, the circuit is completed, right? So at the terminals, it will always be giving me this IL will always be equals to IS. At the terminals, this current is going to remain as that of IS irrespective of whatever is the voltage across the terminals. Whatever may be the voltage across the terminals, this current is not going to get changed, right? That means it is having an infinite internal resistance, right? That's why if its internal resistance is infinite, that means the complete current will flow through the load terminals. Whereas practically that doesn't happen. Practically what used to happen is an practical current source used to have internal resistance, but that used to be a very large value, right? It used to be a very large value and would be shown in parallel, right? Why to be in parallel? Because in this case, now the current has to be divided. It has to be shown in parallel. In series, the current used to remain same, right? So the internal resistance would be shown in parallel. Now, in this case, what is going to happen? Now, I have connected a load, so I'll be having a voltage. As we keep on increase the load, the voltage may increase or decrease according to the variation in the load. Now, what will happen? The current which is flowing is, say, IL. This time, can I say that IS is going to remain as IL? Can IS be equals to IL be equals to IS? No, because now this is the total current. A small amount of the current will flow through this internal resistance as well, right? Which is a large value. So obviously this current which is flowing in this internal resistance, say IN, this is going to be very small. So major of the current is going through the load terminals, but a small current is being received by this resistance, internal resistance. That's why now this time IL is not equals to IS, but that is equals to IS minus IN. Right? So once again, in case, if at all, I plot the characteristics for an ideal and a practical current source, it will be IS versus V. In this case, in case of an ideal, I used to have a straight line, right? There will not be any change in the IS. It will always be equals to, my IL is also always be going to be IS. But in case of a practical one, in this case, I'll be having this drooping characteristics. So this is the characteristics being shown for a practical current source. So what conclusion we can derive from these two? The conclusions we can derive is for an ideal voltage source, if at all I once again go with this, an ideal voltage source is having zero internal resistance. There is no internal resistance. So for an ideal voltage source, the internal resistance is zero, whereas for a practical voltage source, we used to have a small value, right? But in case of an ideal current source, the internal resistance here, that used to be infinite. But in case of a practical current source, we used to have a large value of internal resistance, which will be shown in parallel, right? Now coming to dependent sources, like we were just discussing earlier, what we just see, the symbols what we have seen, those are all for the independent voltage sources and current sources or the sources. Now here we are going to discuss the dependent sources. The voltage or the current delivered by these dependent sources are actually depending on certain other circuit parameters, and hence they are being called as dependent. They may be depending upon certain circuit element voltage or their current. They can be classified in 4 as we will be going along these with the circuits. So the very first one is VCVS, that is voltage controlled voltage source. So in this voltage controlled voltage source, the voltage of the source that depends upon the voltage across the another branch element or the terminal, and it is denoted by the following symbol. If you just see here the symbol is, it's a rhombus shaped source which will be represented with the polarities, and its value is given by certain kV, where this K that depends upon certain other circuit element voltage, right? So this is depending upon certain other elements voltage. So that's why we are calling it as voltage controlled, or it is also being called as voltage dependent voltage source. Similarly, we are having voltage controlled current source or voltage dependent current source. Now, once again, if you see the symbol, it's a current source. Current source is always represented with an arrow. So this will also be represented with an arrow, but not with a circle, as we have seen in case of independent. In case of independent, it will be represented by a circle, but in this case, it will be represented by a rhombus and an arrow. And its value is now, it is a current source, right? But it is depending upon certain other element current, right? This is a voltage controlled, its value is depending upon, it's a current source and its value is depending upon certain other element voltage. So it is a voltage dependent current source. So it will be given by certain kV. The third one, that is current controlled voltage source. Once again, it's a voltage source. So it will be once again, and that too dependent. But this time it is dependent upon the current flowing through certain other circuit element, right? So it will be represented by certain rhombus with certain positive negative polarities and then Ki. Then this is current controlled current source. So it is, in this current controlled current source, the current source is dependent on the current of other branch, right? It is once again denoted by, its current source would be represented with a rhombus and an arrow, and its value is given by certain Ki. Now coming to the most sought out topic in this first unit, which needs to be covered, and the sources, is generally what used to happen while going for the analysis or analyzing the circuits using KVL, KCL, or rest of the theorems we are having, and let that be Thevenin's or Norton's or superposition. Sometimes while resolving the circuit, we feel a need that instead of this particular voltage source, if it would have been a current source, the circuit could have been resolved easier, right? Or the number of meshes are going to get reduced, or the number of junctions are going to get reduced while going for the analysis. So the same can be done, right? That is being called as voltage to current source transformation, and the reverse is also possible. That means we can convert or we can transform a current source into a voltage source. So first, going with how can we transform a voltage to a current source, right? So let's consider a practical voltage source, right? If it is a practical voltage source, that definitely it is having certain internal resistance, which is shown in series. So I'm having a voltage source having its internal resistance as R internal and certain load resistance, say RL, and the current flowing through that is IL. Now, while resolving, I feel like if at all I would have been having a current source instead of that, the circuit would have been resolved, right? The number of the resistance could be merged, or the value of the current sources, and having more current sources in parallel to it, so those can be resolved easily. So I can be transforming this voltage source into its equivalent current source across the terminals. Across the terminals, these are the terminals, the load terminals. I can transform this, a voltage source, and a internal resistance. This is V, this is R. So obviously, the current I'll be getting, the value, say, presently I'm saying that value, I can be transforming it into a current source having I as the value. We'll be deriving what will be the value of this I, having the same amount of internal resistance which was connected in series with the voltage source. This time it will be shown in parallel, across the load terminals, and finally your load resistance. This load current is not going to get varied. That is why we are going for the source transformation. So this is the conversion. Similarly, the vice versa may take place. But before that, to have the value of this current, what will be the value of this I? When it is being transformed, what will be its value in terms of V and R internal? So we can be referring to the circuit IL. If at all I say what is IL? IL is given by the total supplied voltage divided by the total resistance. That is the internal resistance plus the load resistance. Once again, rewriting it, I may be writing it as R internal plus RL, multiplying and dividing both the sides, I mean the numerator and the denominator with R internal. Then once again, V upon Rn internal and taking rest of the resistance together. Now once again, V upon Rn internal, that will give me the current I, right? Multiplied by R internal by the total resistance. So that means, if at all I once again, and the current is going to remain same. We are saying that the current is going to remain same in both the circuits, right? If at all I go with this IL is given by V upon R internal by RL. But what we just go with the simplification, I once again get it up as V upon I internal divided by R internal multiplied by R internal upon R internal plus the load resistance, right? And if at all I give the expression for IL over here, that can be given by the current division rule, right? IL here would be given as the total current I multiplied by the resistance of the opposite branch, which is IN, divided by the total resistance. And if at all we are going for the transformation, then obviously these two IL must be same. This IL must be equals to this IL. Then only the transformation is successful, right? It means what? The value of this I must be equals to V upon R internal. That means this current should be equals to some V upon R internal, where V is this, R internal is this. So just by having the current value being given as the voltage divided by the resistance which is connected in series with it, that can be, we can be having the value of the current, and then the same resistance needs to be connected in parallel across the load terminals. That gets me through the source transformation of a voltage source to a current source. Similarly, the reverse. The reverse is, how can we convert now a current source into a voltage source, right? So the transformation of a current source to a voltage source is just exactly like that. Now once again, consider a practical current source, right? A practical current source is this. A practical current source used to have an internal resistance that to be shown in parallel. So the internal resistance would be shown in parallel across the load terminals, right? Once again, the load current is IL. Now what we are saying is, it is possible to transform an a practical current source into an equivalent voltage source. Once again, what should be the value of this voltage source? We are saying we can be transforming this into a voltage source, having the same amount of internal resistance being connected in series across the terminals. Rest of the circuit is undisturbed. It is going to remain the same. So what should be the value of this current, this voltage? So once again, the derivation can be done. So once again, if at all I go with the derivation, here, once again the load current would be given as the total current multiplied by the resistance of opposite branch divided by sum of both the resistances, R internal plus RL, right? If at all, once again, I go here, what is this IL being given? That will be given by V upon R internal plus R, the load resistance. Once again, equating the equations for both IL and IL, both the sides. Once again, I'll be getting that this V must be equals to I into R internal. That means when I'm transforming a current source, a practical current source in a equivalent voltage source, the value of the voltage source would be equal to the multiplication of the current with its internal resistance, which is shown in parallel. So the mandatory condition, what we just got from all this is, a practical voltage source can be transformed into a current source. What are the conditions? The very first condition is it should have a resistance in immediate series to it, right? Then only it can be transformed. And the value of the current is equals to V upon R, the value which is connected in series. And the same amount of resistance which was connected in series with the voltage source will be connected in parallel with the current source. Similarly, if at all we want to transform a current source into its equivalent voltage source, in this case, the value of the voltage source would be given by the current multiplied by the internal resistance. As this internal resistance would be shown in parallel, the same amount of internal resistance would be shown in series with the voltage source. Once again, the condition is this resistance that should be in parallel with the current source. That is the condition for the transformation. So we have studied enough for this source transformation. So let's have some examples based on the source transformation. So let's go with the numerical. Say, using source transformation technique, if at all I say, find V naught for the circuit being shown. If the circuit is, say, like this, I'm having a 5 ampere current source here. I'm having a 10 ampere. I'm having a voltage source over here. Of the value, this is, I'm having a resistance 10 ohms. Then a voltage source of the value, say 15 volts. And then I'm having a 5 ampere current source with the direction towards right in parallel to a 7 ohms resistance. And this is the V naught we want to have. The thing being asked is, I want to have this V naught, the terminal voltage across the terminals. So this is 5, 10 ampere current source, 10 ohms, 15 volts, the polarity, then 5 ampere towards the right, 7 ohms in parallel to it, and then the terminal voltage V naught. This needs to be done. In fact, the same numerical can be done using the theorems. The same numerical can be done using our basic analysis methods, that are KVL and KCL, node and mesh analysis. But we are going to solve it using source transformation technique. How to have this output voltage using a source transformation technique. So we need to see where the source transformation techniques can be applied. So just see this current source 5 ampere. This current source 5 ampere is having a resistance of 7 ohms, which is directly in parallel to this. These two are in parallel. That means the source transformation is possible. Okay. Once again, what about this? This is a 5 ampere current source and a 10 ohm resistance. Once again, the source transformation is possible. The condition is, whenever we are having a resistance which is directly in parallel with the current source, the source transformation can be done, right? It will act like the internal resistance of the current source. So I can be transforming them. When I transform this 5 ampere and 10 ohm, what will be the value of the voltage source? We have just seen the value of the voltage source is V is equals to I into R in. That means the current multiplied by resistance. So that value would be 5 tens are 50 with the same amount of resistance connected in series. So this circuit becomes, the same circuit becomes here. We are having now 10 ohms and 50 volts. But what will be the polarity? The current source was moving upward. It was heading upward. The arrow was upward. So the battery has to be like this. The value is 50 volts. Once again, this 7 and 5. Once again, this can be converted. The value of the voltage source, that will be once again given by 7 5s are 35. I into R, 35 with the same amount of resistance being connected in series. Once again, the polarity has to be. So I'll be having once again 7 ohms connected in series with the voltage source. The current was heading towards right. So the polarity has to be positive, negative with 35 volts. I'm still facing a problem in resolving. It is not still a single circuit, right? Still, I'm having 10 ampere and 15 volts. Both the sources are there. Both the sources are present, right? And I want to apply KVL for having this output voltage. I know what is the voltage across this 10 amperes. What is the voltage across this 10 amperes? That is just 15 volts. It's in parallel. So applying my KVL through this loop, I'll be coming to know how much is V0. This is negative, positive, negative, positive, negative, positive. So the V0 is going to be 15 plus 50 plus 35. 35 plus 15, that is 50. 50 plus 50, that gets me 100 volts. So the terminal voltage across these two is going to be 100 volts. Going for another numerical. Say, once again, I want to have the voltage across the load, which is just 1 ohm, and having the circuit, which is just shown. Say, if this is 3, this is 1 ohm, and then I'm having a current source of, say, 15 ampere. Then again, I'm having, say, a resistance of 4 ohms, and then a resistance of 10 ohms. In parallel to it, I'm having a current source of, say, 4 amperes. And then I'm having a resistance of 1 ohm. And we need to know what is this V1. That means the voltage across 1 ohm, right? Using once again the technique, the source transformation technique. So once again, if at all I see, where are the chances of applying this source transformation, right? So if at all once again I see where I can transform. Now this 3 and 1, this is in series. So it can be clubbed. 4 and this 4. All the 3 branches are in parallel. 4 and 4. That will get me in parallel. So 4 and 4 parallel, equivalent resistance would be 2. So this is something like I'm having here, instead of this and this, I'm having just 2 ohms in parallel. This is 2 ohms. If that is so, once again, 15 in parallel with 2 ohms, that can be converted. A current source in parallel with a resistance. 15 twos are 30 with the same amount of resistance connected in series with it. Similarly, 10 and 40, 40 amperes, 40 volts with 10 ohms in series with it. So going individually one by one. So here we are having 30 in series with 2. So 2 ohms will be connected in series and upward was the direction. So it is 30 volts. Now again, it is 40 and 10 in series. So it is the direction for the current source, that was towards right. So it has to be positive this side, and then the resistance was 10 ohms and the voltage would be of 40 volts. So this is once again, if at all I see, what we want to know, the voltage across 1 ohms. So that can be known. First, I'll derive what is the current. It's a single circuit. I'll be coming to know how much is the current. So the current through the load, say I, that can be given by This is negative, positive, negative, positive. That is 30 plus 40. The total resistance is 2 plus 10 plus 1. So that gets me 12 plus 1, 13. This is the current. 70 upon 30. This is the current. Once again, what is the voltage across 1 ohms? This is nothing but voltage across 1 ohms. So I need to multiply it with just 1 ohm. So it is going to be 70 upon 13 volts, which is 5.38 volts. I suppose we are done with the source transformation techniques. We have taken 2 numericals also. Thank you all for joining us.